Our speaker is David Ross from Hawaii. He will speak on
So-
Egyptian fractions.
Mel has been giving some talks on ordered groups. And I thought, oh, I've got a result on ordered groups that people in the seminar might be interested in. And so I volunteered to speak about it. And actually, if there's time, I also have, it's going to be using non-standard analysis. And if there's time, I've also got, it's sort of a bonus result, a non-standard proof of something that Mel brought up last week. So we'll see how things go.
Yeah.
Anyway, so, oh, come on.
Oh, yeah, sorry, go ahead.
Yeah, I'm just trying to get my thing to work.
I'm not really available till 4 o'clock. That's when.
Yeah, Mel, you should probably mute your audio. Anyway, so just a reminder, this shouldn't be new for anybody here. An Egyptian fraction is a sum of unitary fractions. Things of the form 1 over, sum of things of the form 1 over an positive integer. These have been studied for a really long time. Fibonacci first looked at them. And in particular, he showed that every rational number can be written as a sum of some unitary fractions with unique denominators. And you can make them arbitrarily long. So the question is, what if you restrict the number of sum ends? So if you're interested in representing a number by an Egyptian fraction with 7 sum ends, for example, and that brings us to 700 years future, to the 1920s, and a pair of papers appeared, one in 21 and one in 1922, in the monthly. Monthly back then was sort of an interesting journal. I mean, not that it's not now, but it's sort of fun to look at papers from the monthly from a long time ago. Anyway, Kellogg and Curtis, well, first Kellogg and then Curtis, consider the Diophantine equation 1 equals 1 over x1 plus on up to 1 over x sub n. And they were interested in bounding the number of positive integer solutions to this, which is the same as counting the number of ways you can represent 1 as an Egyptian fraction with n terms. And Kellogg had made a conjecture, which is about the giving a formula for the maximum value of the x sub i's that can appear in one of these equations or one of these solutions. Curtis proved the conjecture, and actually there's a big chunk of the introduction where he talks about how great his proof is. Anyway, I'm not going to prove anything even remotely like this. This is nothing at all constructive. I work with non-standard analysis, and non-standard analysis equivalent to the axiom of choice. So if you ask me to construct a house, you'd need an ultrafilter to know whether you were inside or outside. So I'm not doing anything like that. But so to motivate the rest of the talk, I'm frequently asked to give introductory talks, and not frequently, but occasionally asked to give introductory talks on non-standard analysis. And when I do that, I always include the following example, which is usually attributed to Sierpinski, which is that if you've got n plus 1 positive numbers, and you look at the equation a equals a1 over x1 on up to an over xn, then that has only finitely many solutions in the natural numbers. And this has a particularly satisfying non-standard proof. So working in a non-standard extension of star R, which also has non-standard extensions of star of n and q, with the property they satisfy all the relevant first order properties, as well as some other ones that I'll talk about later. The actual proof is very, very short. So the non-standard proof goes as follows. Suppose this theorem is false, so that there are infinitely many positive integer solutions to this equation. Then there exists a solution with at least one standard x sub I, and that's one of the magic properties that I'm invoking, which is that if you take any infinite set and take its non-standard embedding, it gets new elements in it. By reordering, if necessary, we can put all of the terms with standard denominators first, and then the ones with non-standard denominators later. If you're a non-standard denominator, it means you're an infinite number. A standard number like a sub r plus 1 over an infinite number is infinitesimal. So this right-hand part is the sum of finitely many infinitesimals, which is infinitesimal. And so what you end up with is some standard real number equals a sum of r many, possibly 0 many, in case all the denominators were infinite, but some finite number of standard fractions, a standard real number over a standard positive integer. So that whole sum is standard plus some positive infinitesimal. But you can't have that. You can't have two standard numbers differing by a positive infinitesimal. So that's the proof that that can't happen. Now, I don't know who this non-standard proof is originally due to. I heard it as a graduate student. I always thought it might be Machover or Hirschfeld. I saw that Ali Khan was in the audience. Maybe he knows, maybe he's seen this before and knows who the non-standard author is.
No, I don't know, David. I don't.
Yeah, it's
very nice.
Yeah, it's a beautiful one-line proof.
Yes, beautiful.
And I never looked up the original paper, but I gave this talk sometime pre-COVID at an AIM workshop where Mel was attending. And when I give this when I give this non-standard introduction to an audience which has standard mathematicians in it, which is almost always when I do it, because why would I give a talk on introduction to non-standard analysis to non-standard analysts? I always prepend the example by saying, look, they're obviously standard proofs of this. For example, Sierpinski was doing his work before the introduction of non-standard analysis. But what's interesting is that there's a non-standard proof, and inevitably somebody comes up and says, oh, I've got a standard proof of this. And in this case, it was Mel that had it. And he got interested in the subject and managed to track down the original paper of Sierpinski's, which I had never done. And that original paper is actually quite interesting. So it was a 1956 paper, and he's got many results about the structure of the set of Egyptian fractions. But by the way, I write here that this result is attributed to Sierpinski. In this form, I don't think it appears in this paper, but close. And the proof certainly doesn't. But anyway, this paper of Sierpinski's has several results about the structure of the set of Egyptian fractions. So, for example, the set of distinct representations of a given number by n-term Egyptian fractions is finite. No sequence of n-term Egyptian fractions is strictly increasing. Sierpinski attributes this to Michalski.
What does that mean? I don't understand. What does
well,
that mean?
So an Egyptian fraction is just a real number, right? You write it out as an Egyptian fraction, but it's really an Egyptian number. So if you've got, it's really a real number rather. So if you've got a sequence of real numbers, each of which can be represented as an n-term Egyptian fractions, it can't be strictly increasing.
You mean it can't be in an infinite term, an infinite sequence?
Infinite sequence, sure.
Okay.
Yeah. No, that's right. No infinite. Sorry, that's right. No infinite sequence is strictly increasing. Anyway, Sierpinski attributes this to Michalski in his paper. So I asked Michalski about this, and he said, "Oh, I don't remember the result, but it's a nice result." And he says, "And I think I know. I think I have a proof of it." And he sent me a proof, but it was actually the same proof that Sierpinski gives. So at least he's consistent. And a lot of other things. What if you allow negative denominators, for example? And Sierpinski shows that if you've got a three-term representation, but no one-term representations, then you actually have only finitely many three-term representations. What else? The set of Egyptian fractions that can be represented with n terms is nowhere dense, even if you allow negative terms. Anyway, the paper is full of stuff like this, as well as some constructive stuff that I didn't take a close. I'm not going to talk about because I don't do constructive stuff. Anyway, so the paper is full of things like that, and it's sort of a nice paper. So Mel and I both were looking at the paper sort of independently, but communicating with each other. And he came up with a generalization, which he called weighted real Egyptian numbers. And we'll see those again below, extending this to more generalized sets of real numbers. I went in sort of a different direction. I took the non-standard methods that you can use to prove that original Sierpinski results, but also the other results of Sierpinski's, and also extended it to other sorts of related Diophantine equations, generalizations of the Kellogg result, this NOM problem. Jeff Ligarius, I don't know if he's here now because I can't see the full list. He had an equation that you can analyze sort of nicely using the non-standard methods. Anyway, that's a while ago. And so the question that I want to talk about today is, can you extend these Sierpinski-like results to general topological groups, not just the reals? And the answer is often yes. And so I'm going to give some examples of that today. Okay. So let's fix a topological group, not necessarily an abelian topological group. And I want to come up with some sort of version of the set of Egyptian fractions. So I start by talking about a subset of the group, and I call it locally cofinite at zero, provided, well, zero is not in the set. And if you take any open neighborhood of zero, the amount of this set T that's left is finite. And so this is the picture I've got. So the whole thing is the group. If I take an open, and the dots are elements of T, if I take any open neighborhood of zero, any possibly infinite part of T shows up in that neighborhood. And then the pieces outside is just finite. So obviously the the unitary Egyptian fractions fall into that category. Reciprocals of the positive integers. If you take any neighborhood of the origin, there are only finitely many outside of that. Okay, so now let's suppose you've got a bunch of these locally cofinite at zero sets. And for any n, you take a look at the sum of the first n of those sets. So you look at the set of all sums of n numbers for which each a sub I is in T sub I. And I'm going to call those, just for the sake of this talk, n-term generalized Egyptian fractions. So if we're talking about the reals, and T sub I is just the sum of reciprocals of positive integers, this is just classical Egyptian fractions. By the way, I allow duplicate denominators in my Egyptian fractions. I know that it's interesting to look at Egyptian fractions where you don't have duplicate denominators.
This setting will accommodate that as well, right? By taking the T's.
Yeah, T1, T2 doesn't allow any of the denominators in well.
No, not so easily. Sorry.
Not so easy. Yeah. And then Mel's weighted Egyptian real numbers were doing something similar, but T sub I would be fractions where the numerator is from some finite set, where the finite set may change from index to index, and the B sub I's, the denominators are from some discrete, possibly infinite discrete subset of R plus. But if you do that, it's not so hard to see that this T sub I is still locally cofinite at zero. And so if we add up n of those, we get what Mel called a weighted real Egyptian number. So those are special cases in the reals for this notion that makes sense anyway in groups with topologies. by the way, I'm not necessarily using the fact, I mean, in a topological group, so I'm writing this as an additive group, and in a topological group, you've got that the sum is continuous in both variables. And it's not so obvious how much of that I really need for a lot of these things. I mean, I have a group with a topology, but right now that's sort of all I've got. I mean, I guess I'm going to use more. I'm going to use the fact that plus is at least continuous, at least separately in the two sides. Okay. Anyway, Sierpinski didn't notice the following result. At least for this is true in the reals. If you throw 0 in for each of the t sub i's, and so you form E sub n prime as the sum of t sub 1 prime up to t sub n prime, where t sub I prime is t sub I together with 0. It's actually a compact subset. And it's true for the reals, and it's going to be true for arbitrary topological group. And once you know that's compact, it easily implies that the result that the set of n-term Egyptian fractions is nowhere dense. And also that the set of n-termed weighted Egyptian real numbers is nowhere dense, because if one of those subsets of the reals was not nowhere dense, then this compact subset, this compact set would have to contain an interval because it's closed. But a non-trivial interval, and non-trivial intervals aren't countable, but the set of these n-term Egyptian fractions or n-term weighted Egyptian real numbers, whichever you're working with, is countable. So once you've got this theorem that the set of things is compact, you get for free the nowhere dense results, at least in the real line. And that's actually, I mean, it's such an easy result. I'm going to show it to you later, but not yet. Okay. So the next thing I have to do is review non-standard analysis a little bit, and I never know how much of that to do when I've got an audience that's seen my earlier talks, and I think most of the people in here have seen me do this before, so I apologize. So we've got a standard universe. Non-standard analysis has the following setup. You've got a standard universe, and it's got all the things you want to talk about. So it's got the reals, it's got the natural numbers, it's got individual numbers as sets, but it's also got individual numbers like 0, 1, 2, pi, e, square root of 2. Power set of the real numbers is also just an object in the standard universe. We're talking about groups. So our group might be in the standard universe. The topology on the group is in the standard universe. The ordering less than or equal to is in the standard universe. And then we've got an embedding of all of those into some kind of non-standard universe. And for every object in the standard universe, there's the star of that object in the non-standard universe. So those are just a bunch of objects living in the non-standard universe. And that non-standard universe in the embedding should have some nice properties. And among those nice properties, we've got a property called transfer. And that says that every first order statement that's true in the standard universe is true in the non-standard universe, and vice versa, as long as you replace the standard objects by their stars. And then there's a notion of saturation. And there's lots of things that you could put here. I'm just going to do what Keith Stroyan called this polysaturation. It's sort of a joke. But if you've got a collection of elements in the non-standard universe, which are not necessarily stars of things, but they might be definable by stars of things, the term that people in non-standard analysis use for that is internal sets. So you've got a collection of these sort of nice sets in the non-standard universe indexed by a relatively small set. And what I'm saying here is that it's indexed by a standard set. So if this collection has the finite intersection property, every finite set of these things has non-empty intersection, then the whole thing has non-empty intersection. So there are various forms of saturation that you could write down. This is a relatively weak form of saturation, but it's enough. And it's easy to construct non-standard models. Easy, I put in quotes. Easy for logicians to construct non-standard models or non-standard universes that have these properties and some other useful properties. Okay. And just to review some things that are true in such a model. So if you have any set G, star respects finite Boolean operations, star of the empty set is empty. If you look at the star of the union of two sets or star of the intersection of two sets, then it's the star of the star of the intersection is the intersection of the stars. If you've got the collection of n tuples where n is finite, star of the of G to the n is the same as taking star G and taking the n tuples from that, and so on. And it's important that I'm saying finite Boolean operations. This doesn't hold anymore for infinite Boolean operations. But the reason it's true for finite Boolean operations is because of the transfer property. Finite Boolean operations you can represent as first order sentences, as finite first order sentences. So anything true in one is true in the other. If this were infinite, if we're talking about infinite Boolean operations, you'd have to represent it with an infinite first order sentence, and there aren't infinite first order sentences. Okay, what else? If you've got a finite set, the star of a finite set is just basically the set itself. That's because you can describe a finite set in a first order sentence. If your set capital A has elements A1 through AN, you can say X is in A if and only if X equals A1 or X equals A2 or X equals A3 and up to X equals AN. But if A is infinite, then A grows, gets new elements in the non-standard universe.
What's your name for the new elements? Do you have a name for them? Things that are somehow dependent on A?
It's just no, sorry. Yeah, well, it's star A. So you can talk about
the elements in star A that aren't in A. What do you call them?
Non-standard elements. I mean,
yeah, but there's a way they depend on A. That is to say, what they have is they're sort of things
you can
that
write
satisfy.
it this. I mean, you can write it this way: if A is given by a formula, then the elements of star A satisfy the same formula. So you would call them elements of star A minus A.
Okay, you don't have a special name for them.
Well, the non-standard elements. Sometimes, I mean, really anything in star A should be thought of as a non-standard element because technically speaking, it's in the non-standard universe, but you can think of the standard universe as embedded in the non-standard universe. So often we just call them non-standard elements. Non-standard elements of star A. I mean, there exists people who work with non-standard analysis that kind of view themselves as mathematicians embedded in the non-standard universe. So for them, the mathematical universe is the non-standard universe. And so the question wouldn't even make sense for people who work. It's called internal set theory. People work in that form of non-standard analysis. For a mathematician in the non-standard universe, for a non-standard mathematician in the non-standard universe, the question doesn't even make sense. He's just seeing A. What we see as star A, he would just see as A. Anyway, so if star G is a group, well, if G is a group, then star G is a group. In fact, it's a star group, but the group operations are first order. So not only are you a star group, you're also a standardly a group. So if you're a non-standard man, if you're us and we're standing outside of both these universes, we see it as a real live group. But internally, the internal non-standard mathematician also sees star G as a group. It's interesting because for us, as a standard group, it's closed under finite addition. So if you have finitely many elements, A1 through AN, A1 plus A2 on up to AN is in the group. But it satisfies more. If you've got an internal star finite set of elements, so you've got a set of elements which is indexed by a non-standard integer, that sum is also in star G. And that's sometimes useful, but it's not going to be useful today. Anyway, it's a group with the same addition and the same identity. Star is an isomorphism of the original group into star G. And star respects the addition and inverse. In this case, it's an additive group, so negative. So it respects those operations. And again, that's all by transfer. And finally, we'll sometimes be talking about an ordered group or a partially ordered group with some kind of order on it. And if A is defined in terms of the operations on G, including the ordering operation, so if A is a set of elements satisfying a certain equation or set of equations or inequalities, possibly with parameters from G, then star A is the subset of star G satisfying the same equations or inequalities. And again, that's by transfer. Now some topological properties. So, and this is true for any topological space with a topology Proctor T. For any element of the original space X, you can define a thing called the monad of X. This is the elements which are infinitesimally close to it. So the monad of any X is the intersection of all stars of open sets. So you think about the real line, you think about 0. You take a look at the stars of sets of the form -1 over n to 1 over n, where n is a standard integer. And you take a look at the intersections of all those things. That's called that would be the monad of 0. It's the things infinitesimally close to 0. And this set is non-empty by the saturation assumption. If we start with a Hausdorff space, if we have two distinct elements of X, then their monads are distinct. That's actually a characterization of Hausdorff. We can write the near standard elements of X, NS of X. That's all just the union of all the monads. That's all the elements that shows up near one of the standard elements.
If X is compact, are there any elements that aren't near standard elements?
No.
Oh, okay.
Yeah, no. And that's actually a characterization of compact. That'll be on the next screen. So if you've got a near standard element, we use ST of Y, the standard part of Y is what that's called, to be the standard element it's close to. So we've got up in the star X, we've got some subset, possibly all of star X, but some subset called the near standard elements. And then the standard part map takes every near standard element, it rounds it off to the nearest standard element. And given two elements of the near standard space NS of X, we say that they're infinitely close to each other if they have the same standard part. So this is a generalization to arbitrary topological spaces of the intuitive notion of how the real line works if you've got infinitesimals in the real line. And here the near standard elements would be the finite elements of the real line. Now go back to G being a topological group with this topology. Then this turns out to be a subgroup of star G. Standard part is a group homomorphism. The following are true for any topological spaces. If U is in G, being open is equivalent to saying that the standard part inverse of U is a subset of the star of U. Or the monad of G is in the monad, or is in the star of every open set containing G. So if you have an element, a standard element, and you've got an open set containing that standard element, and you look at something in the non-standard universe infinitesimally close to that G, it's going to be in star of U. So that's true for open subsets of G. In fact, that's a characterization of open subsets of G. Similarly, if you've got a compact subset of G, being compact is equivalent to saying that for every element of star G is near standard. I'm sorry, every element of star K rather is near standard. So if the whole space is compact, that means every element in the space is near standard. And this is sometimes called the Robinson compactness criterion. So to prove a set is compact, what you do is you take an element of the star of that set and you show that it's near some standard element. And it's nice because it makes the notion of compact really feel like it should be compact if you're not too far away from standard guys, where everything's sort of close in. Okay, so that's the introduction to non-standard analysis, which some of you have seen before. I hope that's enough to follow. Okay, so let's recall that T is locally. First, maybe I should get a watch or a clock or something here. Okay. T is locally compact, cofinite at 0. If 0 is not in T, but every open neighborhood U of 0, T minus U is finite. And it's not too hard to see that using the non-standard terminology, if X is in star of T, either the standard part of X is one of the finite guys in T, or if you're in star T and you're not one of the standard elements, that puts you into the monad of 0. So the standard part of X has to actually, I'm sorry, this should be standard part of X equals, oh, come on, pen right. Should be an equals.
You're not using the concept of infinitesimal in this setting?
Well, I sort of am. I could say if X is in star T, then either X is in T. Oh, and this shouldn't be standard part of T. It should be X is in T, or the standard part of, which is to say the standard part of X is just X, or the standard part of X is equal 0, which is the same as saying X is infinitesimally close to 0. I typed this thing up, and I think I had both ways of writing it in my head, and I just mixed and matched. Okay. Anyway, that's pretty easy to see from the definition of monad, basically the definition of being the standard part being 0. So here's this theorem that I had before. If you throw 0 into each of T1 through Tn, and the T1 through Tn's are locally cofinite at 0, then the sum of those things is compact. And so here's the proof. You take any element of T1 prime plus on up to Tn prime. That's an element of the star of T1 prime plus ... plus Tn prime. But the star of the sum of sets is the sum of the stars of the sets. That's from transfer. And the star of T1 prime, any element in T1 prime is either itself or 0 from this note. And that's true for each of the T sub I primes. So this is just the sum of some either standard elements or zeros. And that means that the standard part of X is in E sub n prime. And so E sub n prime is compact by the Robinson compactness criterion. So it's pretty trivial. And that gets you the nowhere dense results in the real line for free. And most of the results sort of have this sort of flavor. So the question is, what results still hold of the Sierpinski results still hold for these groups? Well, the first one is that if we have T1 through Tn are locally cofinite 0 and nowhere dense in G, then the sum is also nowhere dense in G. And by the way, while the theorem I just wrote down proves this for the reals, it doesn't prove it for arbitrary groups. If you start with a discrete group, it's not going to work. So you have to prove this a little differently to get the general case for groups, but it's not super hard. Another result, which again is one of Sierpinski's results for Egyptian fractions. If G has a representation as the sum of 3 unitary fractions where the denominators could be negative, then it has only finitely many representatives in, well, in this case, negative doesn't really make sense, right? We're just talking about any locally cofinite sets T1 through T3 in our group. Then G has only finitely many representations in E3, or it equals 0, or it's in T1 union T3. It's in either T1, T2, or T3. So that's the natural generalization to these things of the Sierpinski result. Suppose we're a linearly ordered group. So we're an ordered group where all elements are comparable. And suppose also that the order respects the topology in the sense that if you take any group element G, if you look at its predecessors in the group, it's open. Now let's suppose we have locally cofinite subsets of the positive cones. So they're all non-negative in the sense of this inequality. Then no sequence of elements of E sub n is strictly increasing. So this is the generalization of the Michalski result.
Yeah, and again, it means no
Infinite
sequence.
Sequence. Yeah. And finally, let's suppose you've got a partially ordered abelian group, and you start with sets locally cofinated zero subsets of the positive cone of G. Then the number of n-term representations of any element of E sub n is finite. And some of the proofs go through. The proof of one has to be changed from the standard setting or from the generalized standard setting. The proof of four more or less goes through. The non-standard proof of four more or less goes through. For two, I've got a couple of these. For two, so we want to prove that if you take any element which is in E3, it's a sum of three of these fractions, then either it's 0 or it has only finitely many representations, or it's in one of the original sets. So here's how a proof of that would go. So suppose it's in E3, it's a sum of three of these things, it's not equal to 0, and it has infinitely many representations. Well, that means it's got a representation with at least, in the non-standard universe, with at least one non-standard summand. So G can be written as G1 plus G2 plus G3, where G sub I is in T sub I, and at least one of the G sub I's is non-standard. So one possibility is that they're all non-standard. All three of the G sub I's are in star T minus star T I minus Ti. Then G is a standard part of G. Any standard element is its own standard part. That's the standard part of G1 plus the standard part of G2 plus the standard part of G3. But all those are 0. And so that has to be 0. And that's a contradiction because we're assuming that it's non-zero. Second case, G sub I is in T sub I for exactly two of the three values of I. Denote the remaining value by J, and then the standard part of G, again, is standard part of G1 plus G2 plus standard part of G3. And two of these are 0. Only G sub J is something non-zero. And so two of them disappear, and that's G sub J, which isn't T sub J because it's standard. And the third case is that G sub I, only one of the G sub I's is non-standard. The other two are standard. So we can write G sub J in terms of the other ones, and I've not been assuming that the group is abelian here, so that's why I'm writing it three different ways. But you could, either way, you can bring the other two elements to the other side of the equation. The left-hand side is a non-zero infinitesimal. The right-hand side is a standard element, and so that's a contradiction. So again, this proof is really quite easy just by inspection, and more or less the same argument as the original non-standard Sierpinski argument. Three is kind of interesting. So this is the fact that there's no infinite increasing sequence of elements if we're starting with elements the positive cone. So first of all, it suffices to show that every infinite subset contains a decreasing sequence because if you had an increasing sequence, this would say it would have to have an infinite increasing sequence. This would say it would have to have an increasing decreasing sequence. So let's show that every infinite, which you can't. So let's show that every infinite every infinite subset of the set of n-term Egyptian fractions contains a decreasing sequence. So first of all, since S is infinite, by that non-standard property, it's got to contain at least one non-standard element, while at little s. And if you take the standard part of any such thing, it's got to go down. And that takes a little bit of writing, but not very much. Basically, everything that contributes to G either drops down to 0 or stays the same. So in any event, if their inequality is respecting the standard part map, then it drops down. And so here's how we define the decreasing sequence in G sub m. First of all, we look at the things that are less than x. If we take it star, it includes G. So that means that the star of A sub 1, the star of the things that are less than, I'm sorry, the things that, I'm sorry, we start with the things that are bigger than G. This is a standard set, but I'm defining it in terms of, so I'm defining it in terms of the standard element G. So I look at the things that are bigger than G. If we take it star, it includes this S. So we know that star of A sub 1 is non-empty, and that means that A sub 1 has to be non-empty, so that there's at least one element of A sub 1. We call that G sub 1. Now let's suppose we've defined G sub 1, G sub 2, G sub 3, and this is going to be a decreasing sequence. So G sub m is the smallest one we've defined so far, where G is less than G sub m. We look at the set of things that are bigger than G, but also less than G sub m. That's an open set. We take a star of that. We take U isn't, this U is an open set anyway. We take the star of this thing, that's this collection, the star of this first part of the intersection, together with star U. Okay, so this should be just a U, not a U of this thing should just be a U right here, not script U sub G sub m. Since that's open when we star it, S is in the star of that, but it's also in the star of this part. So it's in star of A sub m plus 1. And so star of A sub m plus 1 is non-empty. So A sub m plus 1 has to be non-empty. So it has an element G sub m plus 1. And that gives us then a decreasing infinite sequence from S. So I'm going back and forth to the non-standard model and out of the non-standard model to get my sequence. Anyway, that's the proof of 3. So it's interesting, and from the point of view of that it does have this going in and out of the non-standard model. It's a little bit, there are non-standard proofs of Ramsey's theorem that have sort of a similar flavor to that. Anyway, so these sorts of results are relatively straightforward with this concept of this generalized Egyptian fraction using some of the same kinds of arguments. Some obvious questions. Well, the first obvious question, which isn't down here, is this just the right notion of Egyptian fractions for topological groups? I don't know. It's the one that seemed natural to me. Next question. There are a lot of results. There are a lot of generalizations of the notion of Egyptian fractions and of these Kellogg equations in particular, which have been well studied and for which the non-standard methods give a lot of insight. So for example, you can generalize the Znam equation to look at a sum of terms where the numerators are real numbers, the denominators are every possible product of the variables x1 through xs. And you can ask, what do the solution sets for this kind of equation look like? And it turns out you can prove relatively simply that the equation has only finitely many solutions in the natural numbers. If and only if for every I in the index set, for every variable, it has at least one place where it shows up non-trivially. There's at least one term which includes that where the numerator is not zero. So you can ask, are there interesting variants of these results? This is not easy to formulate, or not obvious how to formulate this for a general topological group, but maybe it is. And are there interesting variants of such results for the general groups? Is result 3, which I use for a linearly ordered group, about increasing sequences. Is that true if you just have partially ordered groups? Does the last result, which I didn't prove here, oops, about the number of n-term representatives being finite, is that true for non-abelian groups? I don't know. So there are various questions you can ask. And finally, a bonus theorem. Last week, Mel quoted the result that if you're a group and every finitely generated subgroup has a left order, then G has a left order. And if every finitely generated subgroup of G has an order, then G has an order. I left off parentheses here. And that actually has a very easy non-standard proof. So of course, if G is finite, it's trivial. So suppose G is infinite. By the appropriate form of saturation, you can find a star finite set H in star of G, where G, which contains every standard element of G. This is a property. So there's a guy named Michael Richter, who once said that non-standard analysis is the art of making infinite sets finite by extending them. This is an easy consequence of saturation. So up in the non-standard universe, we've got some subset of star G, which looks finite to the non-standard mathematician. It can be put into an internal one-to-one correspondence with, or the elements can be enumerated as little h sub 1 through little h sub some non-standard positive integer. And it contains all the elements of the original group G. They all show up in there somewhere. So in the non-standard universe,
because non-standard positive integers are actually infinite. Yes.
Yes, that's right. That's right. That's right. So that's why it's not really a problem. But in the non-standard universe, we can look at the internal group generated by star G, and you can write that down formally for every group and every subset. There exists a group which is a subgroup of the original group, and which contains the original subset, and which is also contained in every group.
requires a first order theory that deals with sets.
Yes.
I mean, you need a more complicated first order theory than the usual first order theory.
Absolutely. You can't do this just working in an elementary extension of the first order theory of groups, of a group. If you have
You need some sort of different types of variables, right?
Well, you don't necessarily need different types, but in the non-standard universe, we have objects representing sets. So we have the real numbers as elements, for example, but we also have the set of real numbers as an object. And so if you the language of the standard universe will have names for every, I mean, basically you can think of it as working in the language of set theory. So, but we have names for every standard object. And so we can talk about them all using first order sentences. You can write down, if you have a subset of your group, your subset A of your group, standardly in the non-standard universe, you can say for all X in star A, something is true. So yeah, that's sort of what the Robinson approach to non-standard analysis brought to the table over what Skolem was doing 40 years earlier, is you sort of simultaneously extend everything in your universe.
You allow, basically, you sneak in the second order theory, higher order theory through the back door, okay?
Kind of. You can't talk about all subsets of the non-standard integers. You can only talk about so-called basically definable subsets of the non-standard integers. You've got a set there called the star power set of the natural numbers, but the star power set of the natural numbers, the star of the power set of the natural numbers, does not contain.
It isn't the power set of the star world.
That's right. It's much smaller. It's got just a distinguished set of subsets, basically the ones you can somehow define in a first order way. Anyway, in this proof, then you can form the star group generated by this set H in the non-standard universe. So that's a star finitely generated group, and therefore a subgroup of star G, and therefore by transfer of the hypothesis, it has a star left star order. But being an order is a first order concept, and therefore the restriction of that to the original G is just a left order or an order on again my sloppy typing on G. Goes one way. Okay. So that's the 4-line non-standard proof of this result that Mel gave last week. So I'm now curious about other similar results and whether they're also trivially non-standardly. Okay, well, that's it. Here's a set of references. I've got a paper corresponding to this. It doesn't include this bonus theorem. I have a paper. I'm not usually a user of the archive, but I have tried to upload it to the archive, but I didn't decide to do that, or didn't think to do that till this morning. So it hasn't appeared yet. So probably tomorrow sometime this paper will appear. Anyway, so that's it.
Thank you. Any questions for our speaker? No. See, David, can you log out of the screen share?
I hope so. Let's see, stop share. Yep.
Good. Kevin, who was there in the room with you?
Yeah, same as last week. Ari?
Yeah. You are distinguished professor, graduate student, guy wandering around?
Yeah, something close to that.
And where in that spectrum are you?
Somewhere close to just person wandering around.
Oh, okay, good enough.
He's auditing a class here at the GC on logic, I guess.
Yeah.
Oh, so this talk was right up your alley, kind of.
Yeah, somewhat.
Okay. By the way, Kevin, you got my chat message?
I did, yes.
Yeah.
I'll be waiting.
I'll try to write down and send it to you tonight. I'm always suspicious of things that get done in a very, very short time. So I like to check it out first. Okay. Thank you, David. Anything going on in the world? Sorry for the interruption at the beginning. Some guy needs to come by and do some work on my house, and he wasn't supposed to get here until 4, and he called up and he said, "I'll be there in a few minutes." And I said, "Well, how about at 4?"
Can you send him to my house when he's done?
Yeah.
A lot of things that need doing.
Actually, I mean, it's like you have to be afraid to send these guys away. So, you know, there was actually, this was like what solved the case on Law and Order SVU, where it turned out the guy who was suspicious was the maintenance guy in some housing project. And the rule was, if he knocks on your door, no matter when, you let him in, because if you say come back later, he might not be back for months. And so he had like free access to everyone's apartment, and that was the key that got him caught. Almost the same thing. Let's see. Who's speaking next week? Here's my schedule. Here we are. Oh, yeah. So next week, it's a guy in Australia who has to either stay up very late or get up very early in the morning, and to talk about the upper asymptotic density of sequences. But he's really not a number theory guy. He's like a analyst, topology type guy. Maybe he's a logician, I'm not sure. So
Who is
he
it?
wrote an interesting paper on the subject, but he said he has to figure out how to translate it into a language that we can understand. Even though he's talking about something that we use all the time. And
By this time next week, we'll have 2 president-elects, I predict.
well, I hope we have 2. If there's only 1, that's bad. Right. So
You don't think we'll have 3? You don't think Jill Stein will also claim victory?
no, I don't think she will. Yeah, we'll see. We'll see. What can you do? Okay, everyone. Be well. See you next week.
Good night.
Good night.